Hey guys, today we're going to look at linear functions versus exponential functions. Now you should be fairly familiar with linear functions because we've done linear functions in 8th grade. We've already done them this year in algebra. You probably did them in Foundations of Algebra last year if you were in there. And so linear functions are just one of those really common things that we use, but exponential functions will be something new. So we're going to kind of look at the difference between those two. So what we know, hopefully, is that a linear function follows the form, you don't have to write this down, y equals mx plus b. And we know, hopefully, that m is your rate of change and your b is your initial value or your y-intercept. Now, an exponential function is not in that form. It is in a form that looks like this. So this is linear right here. There is no b in this one, but it's still linear. This is exponential. So we recognize this is exponential because it has an exponent that's a variable. You see how the x up there is a variable right there? So that makes this an exponential function when the exponent is a variable. So there's some differences in the way these functions grow, and I want us to look at that. So if you had a graphing calculator with you, and you probably don't, maybe you do, I think we can also do this in Desmos. If I'm wrong, we'll change it up. So if we don't have access to a graphing calculator, I can pull up the Desmos online graphing calculator, and I can type this in. So I'm going to look at that very first function, that is f of x. F of x equals 2x. And if you had a graphing calculator, you could pull this up in y equals, but because I don't, I'm going to do that with it. Once I have it typed in, I can push that little gear-looking setting thing. Let me go back because y'all can't see what I just touched. I'm going to push this right here. Wrong button. I'm going to push this right here. That little gear setting thing. And by pushing that, I can create a table. So I did that, and then I pushed this thing right here, and that sets up a table for me. So if I'm going to fill in the table that they've given us here, I need my table to go from 0 up to 5. So I'm going to go and do some modifications on this. I don't need this particular point, but I'm not really going to delete it. So 0, 1, 2, 3, 4. So it's a little bit different than the table on our graphing calculator. The table on the graphing calculator, we can just scroll. This one, we have to fill in the input so that we can get the output that we need. So I filled that in, and now I'm going to transfer those values over to the table that's here. So at 0, my function is at 0. At 1, this function is at 2. At 2, I'm at 4. At 3, I have 6. At 4, I'm at 8. At 5, I'm at 10. All right, so then I'm going to put the other one in. It's 2 raised to the x. So clear that. Technically, they call that one g of x. It doesn't really matter what we call it, but to make our video legit, g of x. And I'm going to go 2 raised to the x power. And so there's the graph of an exponential function. It is not a line like the other one was. It's this curve. I can still pull a table for it. So I touch that little gear, and I'm going to touch this table button right here. And that's going to pull up that table for me. I need the same values for this table. So 0, 1, 2, 3, 4, and 5. And now I have values that I can fill in for the exponential function. So I'm going to fill in at 0, I'm at 1. At 1, we're at 2. At 2, it's at 4. At 3, it's at 8. At 4, it's at 16. And at 5, it's at 32. Okay, so there's my information for both my linear and my exponential function. Now, I want you to think about, when you look at this, how our data changes from one point to the next to the next. So you need to think about, how do you get from 0 to 2, and then from 2 to 4, and then from 4 to 6, and then from 6 to 8, and then from 8 to 10. There's a pattern. What pattern do you see in that? And so hopefully in your brain you're looking at that and you're saying, oh, well, they're just adding 2 every time. Plus 2 from 0 to 2. 2 plus 2 would bring you to 4. 4 plus 2 would bring you to 6. 6 plus 2 brings you to 8. 8 plus 2 brings you to 10. That's what we look for in a linear function, an addition pattern. Something where they're adding or subtracting the same amount to move from one point to the next. For an exponential function, though, the pattern's a little bit different. Check out your exponential function and see if you can see what it's doing to move from one to the next. So we go from a 1 to a 2, but then we change from 2 to 4, and then we change from 4 to 8, and then we change from 8 to 16, and then we change from 16 to 32. So if you're looking for an addition pattern, well, from 1 to 2 would add 1, but 2 plus 1 does not bring you to 4, so it's not an addition pattern. So then we're going to look for a multiplication pattern. Well, 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So instead of a plus 2 pattern, we have a times 2 pattern. That's what you look for as a characteristic of an exponential function. So linear functions are going to grow by addition or subtraction. Exponential functions grow by multiplication or potentially division. We'll still think of it as multiplication, and we'll talk about that in a minute, but that's kind of what we're dealing with this. So, down further on the page, they ask you to tell what you recognize about the graph. We're not going to take the time to graph both of them on that little bitty coordinate plane down there because you can just look at them graphed in Desmos, and there's no need for that. But I do want you to recognize the addition pattern on that linear function and the exponential pattern on the other. All right, turn the page. Now this one gives us, well, look at the top first. At the top, there's a note about exponential functions versus linear functions, and I want you to highlight or circle or underline a little piece of that. So I want you to remember that an output for a linear function will change with addition, and then an output for an exponential function will change with multiplication. We need to make sure we recognize that. The amount that it changes by is called its growth factor. And so it's going to be important that we can pick up on what that number is going to be. So let's pan back down here. Here they give us a worked example of a table that's already been completed. And then they're looking at what is the additive step and what is the multiplicative step for each function. So basically they're just looking for the pattern. So when you look at the linear function, remember the one that's in mx plus b form is linear. So for that one, that's this. And the one that has that x as an exponent is exponential. So in that linear function, we should see an addition pattern. What pattern do we see in that function to get from 4 to 7, and then from 7 to 10, and from 10 to 13, and so on? Hopefully you're recognizing that as a plus 3. 4 plus 3 is 7. 7 plus 3 is 10, and so on. So that's our additive step for that function. So if you see where it says what's the common additive step, they have add 3. And then in the other one, when they look for the multiplicative step, well, to change a 4 to a 12, and a 12 to a 36, and a 36 to a 108, and so on, that's times 3. And they're not always going to give you back-to-back functions that are the same, but multiplication versus addition. But this particular situation does that. But it's a common multiplicative step of multiplying by 3. And so that's what you're wanting to pick up on that. So take a second, pause this video, graph both of these in Desmos and fill in the table, and then see if you can find the pattern that allows you to grow the linear function and the pattern that allows you to grow the exponential function. When you finish that, unpause it, and you can see if you were right. Okay, so when you filled this in, I'm not going to pull up Desmos and all that, but you should have had 5, 9, 13, 17, 21, 25. And then for the other one, you had 2, 8, 32, 128, 5, 12, 20, 48. And so when you went to look for the common additive step in the linear function, hopefully you recognize that they were adding 4 all the way down that table. So it is plus 4, and that made it linear. And for this one, hopefully you recognize that as times 4. 2 times 4 is 8. 8 times 4 is 32. 32 times 4 is 128, and so on. So it's multiplying by 4, and that makes it exponential. All right. Then they give us some data that we don't know if it's exponential or linear, and we're supposed to find out. If you're ever asked to figure that out, and you don't have a whole bunch of, or it's not very obvious what you would be multiplying by, because that happens. Sometimes you're multiplying by strange things. Then another way you can figure out what your growth factor is or what you're multiplying by is to do some division. So you would divide the second y by the first y, y2 divided by y1, for each of the consecutive ordered pairs. Now that word consecutive means back to back. You have to do one right behind the other to be able to find that number. So you can't like do the first one and the last one. You have to do the ones that are back to back to back to back. And so they've given you a worked example of that down here where they take this data in this table, and to find out whether this is exponential, you take the second y, for this one is 7, and divide it by the first y, for this one it's 1.75. And so they've done that right here, and they get 4. And then they go and move to the next pair, which would be the 28 and the 7. You do the 28 divided by the 7. Again, they get 4. Then they go to the next back-to-back pair. That's the 112 and the 28. They did 112 divided by 28 and got 4. And they went to the last pair, the 448 and the 112. And they divided that and they got 4. So because they got 4 for all of them, they can call this an exponential function. And the multiplicative growth factor is 4. So you can find that number that they're multiplying by dividing your y by your x in both. Let's do an example of that ourselves. So here we're going to decide if the data is exponential or if it's linear. And then we will write a function that goes with it, depending on what we find. So when you look at this, the first thing you want to look for is there an addition pattern? Because if you can pick out an addition pattern, you instantly know that it's linear. If there is no addition pattern, then we have to look to see if it's multiplicative. Now, when you look at this and you're like, what am I going to do with these fractions? Because fractions stress you out. You don't have to deal with the fractions right off the bat if you're just trying to decide what type of function it is. I would go to some numbers that you are comfortable with, like 1, 5, 25, so on. Because if I'm looking at that, I can say, well, to get from 1 to 5, I add 4. But 5 plus 4 is not 25. So instantly, because of these 3 points that I have highlighted in green here, I know this is not linear because it doesn't grow by adding. So then I can look to see if I can recognize a multiplication step in there. So from 1 to 5 could multiply by 5 because 1 times 5 is 5. 5 times 5 would be 25. 25 times 5 would be 125. 125 times 5 would be 625. So multiplying by 5 appears to be an appropriate pattern. So once we figure that out, and we're actually going to look at the model in a minute, but an exponential function is always in the form a times b to the x. And the a is the initial value and the b is the growth factor. So initial value of a function is where it is at 0. So this one at 0 is located at 1. So I would put 1, and then my b is 5, because I multiplied by 5, to the x. That's my function model for that one. Now look at b. This one involves some negative numbers, and some people stress out about negatives, but I think we can still get this figured out. If you look at how you change from negative 3.2 to negative 3, that could be addition of 0.2. Or if we didn't know what it was, we could divide it if we were going to try to see if it was multiplication. But let's start with the idea of adding 0.2. Well, if I do negative 3 plus 0.2, I get negative 2.8. If I do negative 2.8 plus 0.2, I get negative 2.6. So this one follows an addition pattern, not a multiplication pattern. That means we write a function in linear form. It's y equals mx plus b. That amount that you're adding every time is your m, because that's the rate of change, the amount it changes. The b is the value at 0, negative 3.2. And that would be a function model for that one. All right, look at problem number 6 down there. It says you try it, but we're actually going to do it together, because the other two were easy to recognize them in our head. This one is not as easy. So it says decide why it can best be modeled by an exponential function. And so we're going to look at that. If you were looking at it to decide if it was exponential or if it was linear, look and see if there's an addition pattern first. From 15 to 12 would be subtract 3, but 12 minus 3 is not 9.6. So because these are not moving by subtracting the same value every time, we know it can't be an addition pattern. So then we have to check for the exponential by dividing the y2 by the y1 in each pair. So like for the first 2 points here, 0, 15, and 1, 12, I'm going to do 12 divided by 15. Then I do the next points, 9.6 divided by 12. Then I do 7.68 divided by 9.6. So it's always the second one divided by the first one in the pair. 6.14 divided by 7.68. 4.92 divided by 6.14. And then, I ran out of space. 3.93 divided by 4.92. And for all of those, if you were to go through and divide them, we get 0.8, 9.6 divided by 12, 0.8, and we would get 0.8 all the way through. So because they have the same common ratio is what that's called, this is exponential. So because it has a common ratio of 0.8. So if I'm going to use this to create a model, remember the a is the initial value. That's the value in the function's at 0. So for this function, that's 15. The b is the growth factor, 0.8. And we always put the x in for the exponent. We're going to do a lot more with writing the functions in just a minute. But for now, that kind of gives you an idea. All right. Whoops. This one gives you some graphs. There's a couple of things I want to point out to you in this box at the top up here. So I'm going to zoom in on that. I want you to highlight or underline or circle or something that a is your initial value, or the value at 0. That b is the base or the growth factor. Could be a decay factor. We'll talk about that in a minute. And that your x goes in the exponent. So the graph of an exponential function will always be J-shaped. If it's increasing, it's exponential growth. If it's decreasing, it's exponential decay. So highlight those couple of things. That's important to you. And if you look at this example they've given you with these already graphed, they take your function and they break down what the pieces mean. So the 2 represents the initial value. That's also where it crosses the y-axis. That's your vertical intercept. So whatever your initial value is will be the point that is on your y-axis as well. So that's where that comes from. Your base or your growth factor is 3. And because my growth factor is greater than 1, that means I'm going to be growing this function. So it's rising from left to right. It's exponential growth. In this one, same situation. They pick out your initial value, which is where it crosses the y-axis. This is your growth factor. Again, it's more than 1, so it's going to cause it to grow. And we can see that because it's increasing from left to right. And then in the last one, they pick out the same stuff, your initial value and your growth factor. And this time, because the growth factor is less than 1, it's exponential decay. And we can see that because our graph is falling. So we're going to do an example of that on the next slide. Turn the page. So look at this function right here. In that, you should be able to pick out that 4 represents your initial value. So the vertical intercept is 0, 4, because your initial value is always where it crosses your y-axis. Your base or your growth factor is 5. And since your growth factor is bigger than 1, this is exponential growth. I can't write that small. I'm just going to put a G for growth. And we can see that it's growing because it's increasing from left to right. In the next one, initial value is 522, which means our y-intercept is 0, 522. Your base is 0.72, which means this is decaying because our growth factor is less than 1. It's going to cause it to shrink. And we can see that because of this. All right, let's look down at the rest of that page. So they give you some information to describe exponential growth and exponential decay functions. And this is going to be stuff that's true for all of them. So remember when we talked about other functions, we talked about the domain and the range of them. And we talked about how domain represented all the possible x values and range represents all the possible y values. So when you're looking at an exponential growth function's graph, and we're thinking about its domain, this line that's graphed, I'm going to highlight it in red, curves down and goes forever this way. It will keep going forever and ever and ever and ever and ever. It's actually continuing to get a little bit lower and further and further and further to the left forever because it's trying to reach 0. It never actually will, but it's trying to reach 0 on the y-axis. So it's trying to move down, 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 down until it hits that spot. But it's never actually going to hit it, but it'll keep going forever that way. On this side, it continues to get wider and wider and wider and wider. It's steeper too, but it gets wider and wider and wider forever as well. So domain for an exponential function is all real numbers, or from negative infinity to positive infinity. That's true for every exponential function ever. The range on every exponential function ever is always from 0 to infinity, because the range, remember, represents your y values. And that red line always tries to reach 0 on the y, but it never actually does. So you're never going to be lower than 0. But it does continue to go up forever. So you will go to infinity on your range, but never beyond 0 because it can't cross the x-axis there. There is no horizontal intercept for any exponential function because it will never cross the x-axis. So the horizontal intercept does not exist. It will have a vertical intercept. It crosses the y. So that's just going to be whatever that point is right there. It's also the value in the A position. A horizontal asymptote is a line that your line does not cross. So if you remember, we just said that exponential function would never cross the x-axis. Well, the equation for this line that is the x-axis is the equation y equals 0. So that line will always be your horizontal asymptote. And then a growth function. Okay, and then a growth function is going to be increasing. And then exponential decay functions are really going to be the same stuff. So they're going to still have the same kind of domain, all real numbers. They're still going to have the same range from 0 to infinity. They're still never going to touch the x-axis. They're still going to have a vertical intercept that is the initial value of the function. They're still going to have that same horizontal asymptote at y equals 0 because they're still never going to cross this line. But the only thing that's different about one that's a decay function instead of a growth function is that it's decreasing instead of increasing. So you'll just want to kind of recognize that. If you see the line going down from left to right, it's decay. If you see the line going up from left to right, it's growth. So if they asked you to describe some things about these two exponential functions, you could take the time to graph them both. And they give you an option up here to like do a sketch of the graph. We're not actually going to do that because you can just graph them in Desmos, and that's silly. So we're just going to write Desmos up there so we remember that that's where we can see a graph if we need it. But I would hope that you can look at these functions and pick out the rest of this information. So what you want to look for if you're looking for initial value, that's the number in the A position. So for both of these, it's 150. The base is also the growth factor. That's the number inside of the parentheses. So for this one, it's 1.25. For this one, it's 0.75. Domain for every exponential function ever is always from negative infinity to positive infinity. I'm really bad at writing with a stylus, y'all. Y'all pretend. So this one, same thing, negative infinity to positive infinity. Range for every exponential function ever is always from 0 to infinity. That's just going to be stuff we want to memorize. The horizontal intercept for every exponential function ever does not exist. It will never cross the x-axis. Now, the vertical intercept does exist. Remember, it's at the initial value point. So if the initial value is 150, our vertical intercept is 0, 150. So the vertical intercept is always that front number there. The horizontal asymptote for every exponential function ever is y equals 0 because it never crosses the x-axis. And that x-axis is located at y equals 0. And then increasing or decreasing, you can graph it and look at it to see if it's rising from left to right, or you can look at your growth factor. And if your growth factor is bigger than 1, it's increasing, and if it's smaller than 1, it's decreasing. So 1.25 is greater than 1. That one's increasing. 0.75 is less than 1, so this one is decreasing. All right, pause this video. Use what we just did on the last page to see if you can fill in the table for this page. Then unpause the video and check and see if you were right. You don't have to graph it. Remember, domain is true for every exponential function ever. So is range. So is the horizontal intercept. So is the horizontal asymptote. So we'll have the same things that we had on the last one on this one. 0 to infinity. 0 to infinity. Does not exist. It will never cross the horizontal axis. Vertical intercept does exist. For this, it'll be 0 to 35. For both of them, because they both start there. Horizontal asymptote for all of them is y equals 0. And then we check our base or our growth factor to see if it's greater or less than 1. 1.14 is greater than 1, so this one is increasing. 0.95 is less than 1, so this one is decreasing. All right, and then this next part asks us to look at how to solve exponential equations. And they give instructions on how to graph them in the TI-84 calculator, which works, and we could solve them in there. But it's more user-friendly to me to use Desmos, and so that's what we're going to do. So I actually took the pages out of the packet that outlined how to do this in the TI-84 because it was too complicated. And all the changing of the window size and stuff was a lot to me. So we're not going to use any of this. We're just going to solve them. We're not even going to sketch pictures of the graph because I'm not really worried about that. Here's what you need to know about how to solve these exponential functions. You take the two sides of them, or the exponential equations. You take the equation like this, and you put both sides, like normally if we were going to graph it in a TI-84, we would put one side of the equation in Y1 and the other side of the equation in Y2 in the TI-84 calculator, and we would graph it and we would find their point of intersection. We're going to do the same thing in Desmos, but we're going to have to break it up ourselves because it doesn't have a Y1 and a Y2. It just has spaces. So what we're going to do is we're going to put this in Desmos, and I want you to make a note of what we're putting in. In the first part, we're going to put Y equals 50. And in the second part, we're going to put Y equals 25 times 1.15. We cannot read that. I'm so bad at writing with this stylus. Try again. 25 times 1.15 to the x. And then we're going to find where they cross. Okay, that's our ultimate goal, is to put those two things in Desmos and then find their intersection. So let me show you how that works. It's not difficult, it just, we got to know how to do it. So here's Desmos. I'm going to type those two things in. Y equals 50. And then I'm going to type in Y equals 25 times 1.15x. Raised to the x. By the way, to make the exponent, you press this button, A to the B, in case you're confused about how to do that. So here's my graph, now that I've done that. And I'm going to need to reactivate Desmos so I can do it. Zoom out until I can see both lines. So you see how I can see both lines, the red and the blue right here? And I want to find their point of intersection. So I'm going to touch that, and I'm going to see that they intersect at 4.959, comma 50. The part of that I'm worried about is the x, because when you're asked to solve an equation, you're finding the x. So our solution to this is 4.959. Now they tell us to round to 2 decimal places, so let's do that. 4.96, technically. Oh, somehow that got attached to Desmos. That's weird. Oh. Well, I don't know what to say about that. I don't know how to undo it. Okay, that's better. So let's do the second one the same way. So in the second one, we're going to put y equals 250, because that's one side of the equation. Oh my goodness, I hit the wrong button now. 250. And then in the second space, I'm going to put, oh, the same thing. So I'm not even going to delete what I have, 25 times 1.15 to the x. And now I'm going to have to zoom even further out. I accidentally clicked off the page and then it reset everything. So if y'all are like, what happened? That's my fault. Try again. Y equals 250. And then y equals 25 times 1.15 to the x. There we go. And our point of intersection, I can just tap right there and it shows me, is 16.475, comma, 250. So 16.475 is our x value. Now they want it to 2 places past the decimal, so I'm going to go 16.48. I keep forgetting to get off the pen. All right, we'll do one more, and then I'll let you guys try. So for this one, same deal. We're going to take it and we're going to put y equals the left side, so y equals 5. And then at the bottom down there, we're going to put y equals... Why are you not touching that? There we go. .86 on the inside. I was trying not to erase all that stuff, but it might have been easier if I had. 0.86, and on the outside I need 10. Desmos is not as easy to use on an iPad, in my opinion. Okay, there we go. That's what I needed. Now I'm still zoomed way out from the earlier one, so I'm going to zoom back in. There's my point of intersection for that one. 4.596, comma 5. So the value of x is 4.596. Again, they want that to 2 places, so 4.96. I did it again. All right, on this page, we'll do the same exact thing. A whole bunch of these. I don't know that we need to do a whole bunch more since we have access to Desmos. So why don't y'all try this page, and then we may leave the next page off. Pause the video, try these, see what you get for your value of the variable, and then unpause the video and see if you were correct. All right, so if you finished them, you should have gotten 10 for the first one, 0.48 for the second one, and negative 1.089, or I guess 1.09, technically be rounded right. Negative 1.09. If we were rounding that correctly. And again, all of that comes directly from Desmos. If you'll graph y equals this and y equals that for both of them. And it doesn't matter what letter you use for your, well, you use x for your exponent regardless of what letter's in there. It's like this one had a t, but you could use an x for that and still get the same value. So anyway, I think we'll skip the next page because I just don't know that there's any need to practice 3 more of those after we've just done 6, and it's as simple as it is. So we'll stop the video right there. If you're confused about any part of this, let me know. Jump on the Google Meet and ask questions or whatever. Otherwise, you should be ready to do your practice. Y'all have a great day. There's